Welcome everyone to session 5. We have 4 talks in this session, starting with learning to see through reflections. This is work by Meiguang Jin, Sabine Süsstrunk, and Paolo Favaro, and Paolo will be giving the talk.
Joint work, as you heard from Meiguang Jin, with my student Meiguang Jin, also Sabine Süsstrunk from EPFL. And unfortunately, Meiguang couldn't be here to give the presentation due to visa delays. So I'll be giving the presentation. I apologize in advance if you have questions about technical details. I may not be able to give you all the details, but we can still try. So the focus in this talk is about glass. Glass is a great material. It lets light through with very little, if negligible, loss. And at the same time, it shields. And indeed, you find widespread use in today's society, from transportation, architecture, and displays in our favorite technology. Now, glass lets light through, that's why we use it, and protects. But at the same time, it also reflects. And when it does that, then what you observe is a superposition of 2 images. And that's a problem for us because then we are not really trained to interpret images when there are 2 superposed, one to the other. So at least evolution didn't have enough time to catch up and cope with it. So it would be interesting then and useful to find a way to separate, to remove this hindrance, the reflection, so that we can better understand the content. So to put it more precisely, what we want to do in this talk is to take a single image, which I call a composite image, and separate it into the 2 layers, which I call background. It's the image that you see behind the glass, and the reflection, which is the image you would see if the background were completely black. Now, this is a very challenging task because we are given a certain amount of data and we want to get twice as much out of it. So it's very ill-posed, and definitely one needs to rely on good priors to do that. So there's been quite a bit of work in this area, a number of approaches. Here I'm just highlighting some of them. So I hope I don't offend anybody who doesn't appear. But this is just to give an idea of what has been done. For example, some methods use multiple images. For example, by exploiting different focus settings so that one can better separate the 2 layers. Or one can also use pairs of images, one captured with a flash, one without a flash. That also helps differentiating them, or using different polarization, or also capturing a video and then using frames from a video where I change the perspective, aligning them, and then based on the fact that the reflection has a different perspective, then I can separate them. Now, all of these works exploit multiple images, while instead we focus on single image reflection separation. So we don't compare to these methods, but we would rather compare to this other group of methods where a single image is used. Now, to use a single image, then you need to really focus on priors that allow you to distinguish these 2 layers. So, for example, in the work of Lee and Brown, they formulated good priors for the gradients of the reflected layer and the gradients of the background image, and then they use that as a cue to separate them. Also, there is some recent work where the reflection could be separated based on the reflection, the double reflection effect that we have in some glass, which creates this ghosting artifact, and which creates a very different effect for the 2 layers to be distinguished. We don't compare to this one because we consider single reflections. So we compare instead to this other method by Arvanitopoulos et al., where a different prior for both the data and the gradients were used, and then solved an optimization scheme. And finally, we compare also to the current state-of-the-art, well, before our work, the state-of-the-art by Fan et al., which uses a deep learning approach. Now, to understand how we can best separate reflections from a background, we first need to have a look at the image formation model. So let's consider a camera, which here shows a simplified version of the image plane and the lens with some aperture. Then we have some glass on the optical path. Behind the glass, we have a background image B. And in front of the glass, we have another scene, which we call the reflectance R. Now, if we have a small aperture, then we have a very large depth of field. Then both of these images are in focus, or say approximately so. So the composite image will be simply the sum of these two layers. However, having a very small aperture means that we need to wait a very long time, so the exposure has to be long to capture good images. So in practice, people use a finite aperture, which then leads to a finite depth of field. And then if we focus our camera on the background, then the reflection will be out of focus. And so in general, it will be an image R convolved with some point spread function H. So our composite image will then be given by the sum of the background image and the blurry version of the reflectance. And this Q, this difference between the blur in the two layers, can be used as a cue to differentiate them and to separate them. So the next question we can ask is, well, if I'm given this image formation model, then can I really distinguish any B and any R convolved with H? Or are there images that actually cannot be distinguished, cannot be separated in an unambiguous way? Turns out that the answer is no. Sorry, yes. There are images that are ambiguous. And this family of functions are the harmonic functions that satisfy Laplace equation. And just to give an immediate idea of what these functions are, take, for example, a function that is a constant, just a constant color image. If you take the second order derivatives, it goes to 0. And this then can also be shown quite easily for images like a slope in X, in Y, or any linear function of your coordinates. Second order derivatives will clearly go to 0. And then, of course, there's many more functions. So why are harmonic functions a problem? Well, because they are invariant to circularly symmetric blur. So if you take those functions and you blur them, they stay the same. And then if you want to distinguish your background image from the blurry version of the reflection, if they are harmonic functions, you cannot tell one from the other because the blur won't differentiate them. And so you don't know if you should associate this harmonic part to the background or to the reflection. And that's a big ambiguity. Now, the part of the images that has the strongest energy is the average color. So that's a very strong harmonic component. And indeed, you can immediately see that I don't know if what amount of the average color should go to the background and what amount should go to the reflection. That's completely impossible to do. However, for other harmonic components that have maybe like a slope or have some variation, we might be able to decide if they belong to the background or to the reflection, or in what amount they belong to one or the other, based on a global analysis of the image, if we look at the entire image. And That means that we need to develop a prior that is not just local, but it is global. So to achieve that, what we suggest is, well, for the average color, there's no way to tell to which layer it should belong to. So let's just decide from the start, we're going to assign all of it to the background image. And so we remove the mean from the reflection. And then for the global prior, then we use a neural network, and we make sure it has very large receptive field so that it observes the whole image, and it can build a prior for that. So that's our strategy here. So to train then our neural network, because that's the approach we're going to use here, then the next step is to have data. And we found that we need to have about 20K to 200K images to train your system. And the data we're going to use would be pairs of composite images and background images, which is the target you want to obtain. And although it's possible to capture real data here, because you could capture an image, remove the glass, and then capture the background, if you want to do that for 200,000 times, that it becomes a bit difficult to do. At least I couldn't see a simple way to do it. So we resorted to then synthesizing real training data, and the purpose was to find a suitable model that then would generalize well to real data. So we explored a number of models to generate the data. Of course, we started with the simplest, which we call the convex model. So you have some alpha between 0 and 1 that then you use to combine the two images, the two layers. Then we, based on our analysis, we employed the, oops, sorry, this was the wrong button. We employed the zero mean model, where basically we remove the mean from the reflection, and we add a small delta to then create some variability in the contrast. This model, however, may have negative values or may have values above the maximum value in the images. It's not really realistic. A more realistic one is what we call the saturation model, where basically we use a clipping function f, which clips to 0, negative numbers, and clips to the maximum value, any value exceeding the maximum intensity in our sensor. And then we have the brightness model, which is the one proposed by Fan et al., where basically the focus is on the negative, say, range of the composite image. So what they do is, instead of subtracting the mean, they subtract some constant so that they make sure that they don't really exceed the maximum value that much. And then this function clips just the negative values. But we believe that our model that has both clippings for the saturation on the high values and the low values has other benefits, like it teaches the network to also do in-painting, which we find quite useful. So we adopt this model, and we show that this actually generalizes better to real data and to the other data sets. Now, a few words on the network design as well. So we design a network that is inspired by the dense net. So we'll have connections that come from earlier layers and then are added as residuals to following layers. To achieve the large receptive field, we also use a resampling strategy, which essentially amounts to having strided convolutions. And also we use a channel-wise network that reduces a lot the number of parameters. I will show the architecture in the next slide. The other element that is probably useful to know is the loss function that we use to train the network. So of course we want our network output. So network is phi, takes as input the composite image I, and then we want it to match the background image. We do that with an L1 loss. And at the same time, we also have here another term, which is the perceptual loss, which is quite widely used for networks that output directly pixel values. And here we use a pre-trained VGG, so we extract some features of the predicted image and some features from the background image, and we want them to match as well. And that proves to be a very useful term as well in our loss. So here's the network. So we have a number of layers that process each channel independently. All the weights are shared. Here you can see a bit the dense net kind of architecture. And then finally, all of these layers are put back together and then added to the input as residuals. Then we have another block that combines all these process layers together in an even better way so that we can add them again as residuals to the input image. And finally, we hopefully get our background image. So here are some ablation studies to show that every component we use has a purpose and has an effect. We use the normalized cross-correlation and structural similarity as metrics. These are probably not the best metrics to measure quality of images, but these are widely used. So at least we have some understanding of what they do. We use as baseline a network where every convolutional layer has 32 channels as a reference. And then we can see that if we reduce the number of channels, we lose performance. If we increase them in what is the final network that we use, then we gain performance. If we go even beyond that, we might start to overfit. So we found that this is a good trade-off. If we don't use dilated convolutions, then the receptive field will be smaller, and then here we lose this ability to have a global prior. So you can see that there is also a loss of performance here. The L1 loss alone also is not enough. So you can see that it doesn't achieve the same quality as when you use the full loss. And even if we use fewer features, you don't get the full performance. Here's also some evaluation to show that the model that we use to generate the data actually has a better ability to make the network generalize. So here is the saturation model is what we use to train, and here's the test we get on a test set, a separate test set with the same model. And here is a separate test set obtained with the convex model. So it's a different model, and we can see that we generalize very well also on this. And also we tested on a data set by the method of Fan et al. And you can see that we also generalize quite well on their data set. Before showing some visual results, I want to also say that the network is quite efficient and also uses very few parameters, which results in a very good memory footprint. It's quite efficient. So let's see some results. Here's some synthetic data. So this is the composite image. This is the background, and this is the reflection. And as you can notice, we have that because this part is very bright, then we have some saturation here, which basically removes content from the background. So the network really has to learn to in-paint in those regions. So this is what we get from Lee and Brown. This is what we obtained from Arvanitopoulos et al. This is what we get from Fan et al. And this is what we get. So you can see that it's not perfect, but it has separated reasonably well the background from the reflection. Here, we don't get all the details of the ground truth, but you can see that it has in-painted in some reasonable way the content. But more importantly, it has separated all the flowers and many of the details from the background. Now, this is on synthetic data. On real data, we have, so this is an image from Lee and Brown, I believe. This is the composite image. We don't have the ground truth. This is the result by Fan et al., the result by Arvanitopoulos et al., Lee et al., and this is what we get. Here's another set of data, real data that we collected, also in this case without ground truth. So this is Fan et al. Lee et al., Arvanitopoulos et al., and this is what we get. So you can see, again, it's not perfect, but we get a reasonably good separation of the two layers. And one last set of real data. So again, Fan et al., Arvanitopoulos et al., Lee et al., and the proposed method. And as you can see, here there is much more content left on the background image, and we can separate that reasonably well. Okay, so there's one very last one with ground truth, but maybe I can show that more quickly. And then you can see that we can separate that. In this case, we had also the ground truth. So in conclusion, the main challenge in the reflection removal problem is that we have these ambiguities caused by these harmonic components. In particular, the average color is a very strong component, and the context ambiguities caused by the other higher order components. And we can directly remove the average color because that leads to, that's an ambiguity we cannot possibly resolve. But in the case of the other ambiguities, we can use a global prior to then separate them, and using a network with a large receptive field and a proper data set, we can do that. So we have shown that our network can perform that quite well, I hope. Thank you, and if you have any questions, we'll be happy to answer.
We have time for a few questions. Yeah. Peyman.
I'm curious what the prediction residual looked like. So if you took your two separated components, you combine them and subtracted them from the input, what would the actual?
It would look, not exactly, but it will look like the reflection, because there is some in-painting sometimes. They might look like the reflection when there is no in-painting. Because
have you tried using that residual to maybe improve the results?
well, we tried many things, yeah, possibly one can impose additional constraints on the residual. As we tried to have the matching of the residual to the reflection, and then the difference to the background. But actually, those things don't go too well with the in-painting part. So we found that this configuration was the one that was performing better. But of course, who knows? Maybe there are some things we have not done correctly, and then maybe one can do it.
Very cool results.
Thanks.
I had a question about the loss function that you used for your neural network.
Mm-hmm.
Combining L1 loss with some like VGG feature loss.
Yes.
Did you, how does it change if you just do like straight L2?
With L2, you tend to get a bit more blur in the results. This is a known result because of the averaging effect of L2. L1 is a little bit better, but really what makes also a big difference is the perceptual loss, which is the VGG part.
Does that limit you in any way?
No, why?
Perhaps the features that VGG learns are good for certain types of images, but not others. It's a big data set, though.
Yes, I think it's sufficiently big.
When you're training your algorithms, to what extent do you check that the training images themselves have like different spatial statistics in terms of the spatial frequencies present in the images from the background and the foreground images?
So we synthetically also blur the reflection layer. So do you mean how we control that?
What I really wondered is how are the spatial frequency statistics different for the background?
Well, the reflection layer is always blurred, and we blur it with a range of blurs, diameters. And that's how we keep them distinguishable. Was that the question?
Yeah, okay. I'm just curious to know how distinguishable they are. I mean, basically, just on the basis of the spatial frequencies in the image.
Well, so locally, you might have ambiguities, but actually, once you go and have a more global prior, then that's when you can really resolve all the difficult ambiguities, which indeed you wouldn't have because the frequencies can be mixed.
I think we'll move on. Any other questions, we can maybe ask them offline. We'll move on to the next talk. Thank you. Thank you, Paolo.
Thank you so much.
Thank you. My name is Hossein Talebi, and I'll be talking about learned perceptual image enhancement. This is a collaboration with my co-author, Peyman Milanfar. The typical way of actually doing learn-based image enhancement seems to be in a supervised manner in most cases in image processing nowadays. We basically come up with a data set of images, usually pair images, and an input and a target reference image that we desire to generate from the input. We do have a model, for instance, could be a CNN model to enhance the image. And the objective is to train this model with some training loss to get as close as possible to the reference image. The problem is that simply using an L1, L2 norm-based losses or even SSIM does not lead to perceptually superior results. So this has been widely known, and as in the previous talk was implied briefly, this has been the issue for different applications in image processing. So what we propose in this talk is simply adding a quality term to your fidelity loss. By fidelity, we mean a full reference loss, could be L1, could be L2, could be SSIM, could be the VGG loss that we're just, the previous speaker was talking about, in which it measures distance between a reference image and an input image. The term that we add is based on a technique we call NEMA, stands for Neural Image Assessment. It's basically a CNN trained for predicting image quality based on human preferences. So this loss term simply is added with a weight in front of it to your training loss. It does not impose any complexity to your enhancement CNN or any model that you use at inference time. So I'm going to talk a little bit about NEMA, show you examples, and then we dive into details. So NEMA is a no-reference image enhancement technique. Basically, you pass an image into NEMA model, and it gives you a score from 1 to 10, 10 being the higher quality, 1 being the lowest quality. You see some images that are basically ranked based on NEMA's score from top left to bottom right. These are some landscape images. So the model tends to assign higher score to images that are more pleasing to human raters. I'll talk about the data and how the data actually is curated. Could be a variety of different types of images, of the same object, different objects. Basically, at inference time, we'll get a score from 1 to 10, and you can, for instance, rank an album. The images that get lower score, as you see, like images from low light scenarios or blurred or noisy images, which does make sense as a perceptual metric. Could be your own personal album and photos. You want to rank them and find pleasing images. You can use NEMA as a signal. This is my co-author, by the way, Peyman. Also, this model is quite sensitive to image distortions, for example, JPEG compression or blur or noise. These images that are shown are basically from left to right. We increase the level of degradation in the image. Basically, we compress the image on the top row more aggressively as we go from left to right. And as you see, the score basically drops. On the second row, you see this similar experiment with Gaussian blur and similar trend with the score associated to these images. Could be a variety of combination of different distortions, compression, blur, etc. added, and then still it's able to distinguish between lower quality versus higher quality images. Could be a burst of images. These images are taken with a few hundreds of milliseconds apart from each other, and as you see, the image with more motion blur and bad framing actually gets the lower score compared to the sharp, well-framed image. Okay, so a little bit of background on research in image quality assessment. We can roughly divide the research to four overlapping areas. One is where we deal with pixel level quality, technical quality of images. What I mean by that is measuring perceptual degradations usually, such as a few examples that I showed you: noise, sharpness, compression artifact, tone, color, brightness, etc. And a little bit higher level is actually, we call it semantic level, which actually deals with aesthetics in images. And basically the problem is measuring beauty and appeal. So this is this probably could be a more content level problem. However, they do overlap, we believe, meaning that pixel level quality could affect aesthetics of images, and content also could affect the ratings that the user might actually give to an image. Also, another two distinctions are: one is a setup of full reference quality assessment in which we do have access to a reference image, you call clean image or reference image. For example, PSNR, SSIM, people have been widely using those metrics. On the other hand, in most practical scenarios, you do not have reference images. So what do? We usually label the data, for instance, with human raters and crowdsourcing, which makes it, to some extent, subjective. So the scope of NEMA are roughly these three areas. So we don't focus on full reference quality assessment. So the data that we used for training NEMA is called AVA. This is from a paper in CVPR 2012. It roughly contains 250,000 photos. Each photo rated by a couple hundred amateur photographers. The way this data was collected was through online photography contests. So each contest has a theme, has some rules. People take photos, upload them, and then rate each other's photos. And then, so at the end of the day, we'll have data, photos with a histogram of ratings attached to each of them. The example I show you here are the mean of these scores for each image for one of these contests. The theme for this contest was stairs, simply. People went out and took pictures of stairs. These are histograms of mean score from AVA for the 250,000 photos. On the left, you see a histogram of mean scores. It's pretty much highly concentrated around 5.5 for a range of 1 to 10. The second plot shows the standard deviation of scores. The mean of standard deviation is 1.4, again for a scale of 1 to 10. And this, the last one is the joint histogram. So as you see, if we were to train a model on the mean scores, it would be quite challenging given that most of the data basically lives close to a 5.5 score. So here's what we do. We basically train a CNN model on the histogram of ratings, on the raw ratings that we get for each image. The architecture that we use are basically, we tried different architectures, mainly relying on object detection architectures, VGG, Inception, MobileNet. These three architectures we tried, and the way we changed the architecture to fit it to our histogram labels is that we change the last fully connected layer, we output 10 neurons, and then we retrain end-to-end on AVA data. So we do not rely on features that are simply trained on ImageNet, for example, 1 million photos for object detection. We retrain again for the purpose of image quality assessment. And I think that's the main distinction between this work and what people do with simply using VGG features. Some examples. On the left, you see a relatively high-quality image with its ground truth and predicted histogram scores. On the right, you see a low-quality image, and in the middle, an image that has close to a score close to the mean of overall data set. We've observed that NEMA is capable of closely predicting the ground truth score. And to support that, we compared performance of NEMA to existing methods out there. And we observed that NEMA based on inception architecture performs the best. Usually people tend to, mostly tend to only report the accuracy on binary classification. We find that not useful at all. In fact, the linear correlation and rank correlation are more useful in terms of comparing the methods against each other. However, we report the accuracy number for our method. So that in terms of complexity, and NEMA only needs one pass of the object detection, only one pass. So that its complexity is roughly the complexity of the underlying architecture used for object detection. It does not require any pre-classification, scene categorization, or multiple passes of the data. So that's the main advantage that, in terms of complexity, NEMA has. So going back to our proposed learning-based image enhancement, now we do have a NEMA score. We can simply plug it into our perceptual loss. We chose to use L2 for our fidelity loss. You can pick anything, as long as it relies on the reference that you wish. We picked 3 different applications to showcase this perceptual loss. One is a tone mapping algorithm, one is image dehazing, and the last one is image denoising. So these methods are obviously differentiable, so we can simply plug in the CNN or the model and train end-to-end. And for enhancement CNN, you could again pick any differentiable model. We picked CAN architecture. CAN stands for Context Aggregation Network. It was introduced quite recently and was used for approximating image processing operations efficiently, and mainly was used for image segmentation. I'll go to a little bit of detail on CAN, and then I show you some experimental results. So CAN basically is a 10-layer network with fixed number of feature maps, 32, and the convolution filters are 3 by 3. However, there's a caveat in there that the dilation rate basically increases as we go through the depth of the network. So the net effect of that is each output pixel becomes an aggregation of several input pixels. So basically the footprint of the filter increases. Right, so some experimental examples of what should we expect. On the left is the input. The second column is reference. CAN trained on L2 is third L2 plus NEMA. You probably don't see much difference, but I have to zoom in here to show you the difference. Input, doing some tone mapping, and then CAN plus L2, L2. You see how detail in the dark area is just popping out, and the color palette looks much better. A few more examples. The overall look of the image on the CAN L2 and CAN L2 plus NEMA globally looks similar, but actually when you zoom in, you start to see how details are much better preserved with simply adding NEMA as a perceptual loss. So I'm simply flipping back and forth between L2 plus NEMA and L2 here to you see the difference. And again, this does not impose any more complexity to the CAN architecture. This is just a training time. With training CNNs, we have observed that there are known artifacts like halo artifacts, ghosting, depending on the filter size. We see that adding NEMA is actually does help to reduce those type of artifacts. Again, going from L2 to L2 plus NEMA, you see that these artifacts are increased significantly. We tested it pretty much on all of Adobe MIT dataset and tested it on faces, on different parts of images, tried to make sure that the improvement is actually quite consistent. This image, again, the color palette looks better when we have the NEMA term in the training loss. Even compared to the reference, even compared to the reference image, the L2 plus NEMA looks slightly better. For dehazing, we did pretty much the same experiment, just replaced our data with dehazing data, left again input, reference, L2, and then L2 plus NEMA. I'm going to show you the cropped images. Input, reference, you can see what the L2 is doing to the sky, and then details in the dark areas, and then when we go to L2 plus NEMA, this happens. So from L2 to L2 plus NEMA, look at the sky, the green artifacts in the sky disappear, and more details tend to appear around this bridge down here. More examples on dehazing. Simply L2 tends to change the palette of the image completely. The reason is, well, this dehazing algorithm is applied on RGB, and the loss L2 does not have much consideration for the palette there. Also we tried it for denoising, image denoising. The idea is to find the best, say, spatial parameter that tunes our denoiser. The higher the spatial parameter, the more aggressive the denoising. So input image noisy, then what I'm showing you here is a plot of scores, NEMA scores versus that spatial parameter. You see that at some point that the score is maximized, and then after that, as the image is more and more smooth, the score tends to drop. So this is the best image that we get from this operation point. And then this is if you simply go all the way and over smooth the image. Of course, you're losing a lot of details, and the image doesn't look as sharp. All right, thank you.
We have time for a few questions. Yeah.
Would it be possible to put this real time into the heads-up display of the consumer camera to rank for people, let's say, to learn photography, to basically watch this course with the learn framing?
Yes, yes. So we tried on 3 different architectures, VGG being the heaviest, the Inception, and MobileNet. MobileNet is exactly designed for that purpose. It's a very light model. You can simply import it into cell phones and use it. And it will work pretty much close to real time.
So here this NEMA is designed to replicate the performance of this predicted image quality of the database. What can you tell us about like the culture of the community of people who created that database? I mean, there are people rating these photographs. What do we know about those people?
These are photography enthusiasts that they do that, basically. And they're interested in taking photos, sharing them, and, you know, rating each other's photos. So they...
Is it a worldwide community?
It's actually the website that these photos were basically used from it's called dpchallenge.com. So digitalphotographychallenge.com. There are a few more that you can find online, but this is probably one of the better known ones that comes to mind. But but yeah, you can check it out. It has close to 1 million photos, actually, this website. You can subscribe, upload your photos, and then get feedback from other photographers. Yeah.
I've noticed 4DP challenge is heavily dominated by Icelandic photographers because it's a stunning place, right?
Sure. Yeah, there are definitely other ones. The photos.net, that's another one that you know, has the very similar structure compared to DP challenge. Yeah.
Do you think that the camera aspect ratio of different cameras play into different training moments for everything?
Yes, we believe that that's the case, and we exploited changing the architecture of our model to get any aspect ratio, meaning that the challenge is being able to implement the fully connected layer after your convolutional layers to be able to adapt it to different sizes. And you can do that. There are tricks that you can basically do that to, instead of resizing the image, which is the case in object detection, you pretty much don't care about the scale. You resize, you pass it through the network. But you can change the network to get, you know, the native resolution and generate a single score for that image. Yeah.
So along with that, if you're doing your square histogram even though you're using the same frame camera.
Sure. Okay, so let me rephrase your question. Would it be possible to use this for cropping images, for example? Yeah. Yes. That's an application that other people have exploited using the AVA dataset, and it has shown some success. Yes.
Can you talk about how you did the hyperparameter selection for how much weight the NEMA loss versus how much weight the LP loss?
Yes, that's a good question. So we actually, we might get some failure cases if you become too aggressive with the weight in front of NEMA. So we simply sweep the values for this parameter to make sure that the fidelity and quality loss are in the same range. So we fine-tune that for these applications, and we kept it fixed across all the experiments that I showed you. Yes.
Have you given any thought to using like more perceptual uniform color space?
We do use RGB, but I hear your point. Yeah, that's potentially an improvement to make basically working in a more perceptually relevant color space in terms of, you know, suffering from color shift, etc., which happens easily in RGB. Yes, that's definitely it could be an improvement.
Yeah, this way. The transformation is linear. That was going to learn it anyway.
Yes, that's.
So if I understand it correctly, like you were trying to mimic the enhancement being done by a certain operation. That was your reference image. Is that what you meant by reference image in your results?
Yes, the reference image, yes. So an operation could be a tone mapping operation which gets an image and generates a locally tone mapped image. Okay. Now we want to get as close as possible to that. However, we don't want to sacrifice perceptual quality.
Right. Okay.
So
I'm just curious, did you do a comparison to say like perceptual, like VGG, feature-based perceptual loss compared to NEMA?
Yeah, so if you actually plug in, simply use a VGG loss, you're going to get all sorts of artifacts depending on what you do.
Okay.
For super resolution, for denoising, you get artifacts. Okay. Then you have to add another term next to it. Okay. However, the VGG still is not trained for perceptual quality. It's for object detection. So you have to retrain to get better results.
Right. Okay. Let's thank the speaker.
Thank you.
Thank you, Kallium, for the introduction. Hello, everyone. My name is George Chen, and today I would like to talk about how we can combine deep learning and physics-based image formation model to solve the problem of motion deblur. And this work is a joint collaboration between Rice University and NVIDIA Research. So first of all, deblurring is a very important topic in computer vision because it concerns both high-level visual inference and low-level image processing. For example, there are millions of blurry cats, cute cats, image and video online that we are neither able to recognize the cat or estimate the motion of the cat in them. And this is really bad. Those cats could be blurred by defocus blur or motion blur. For the scope of this work, we will focus on motion blur, which includes object motion and camera motion. We know that Deblurring method can be roughly divided into two categories. First is the model-based approach that treats the forward blurring process as the convolution of the blur kernel with latent sharp images. Therefore, the deblurring process is essentially to solve the inverse problem of the linear system. And here, estimating the blur kernel is an ill-posed problem. And the incorrect blur kernel estimated can result in severe artifacts in the deblurred image. And even with the correct blur kernel estimation, reigning artifacts from the deconvolution procedure are pretty common. The second approach is the recently emerged data-driven deep learning-based method. In this approach, image formation model is largely ignored. One would just build a encoder-decoder network and feed the network thousands of blur-sharp image pairs for the training. And however, the problem with this approach is that sometimes it produces only sharp-looking images which contain some artificial high-frequency texture, but such sharp image may not be faithful to the ground truth. And such artifacts are even more common in the now very popular generative adversarial networks. And at the same time, deep learning-based approach requires large training data set and may not generalize very well on the data outside the training sets. So the goal of this work is to bridge the gap between the two approaches and propose a framework that leverages the advantage of both methods and overcomes the limitations. An intuitive way to look at the problem is that if we assume that there is an underlying manifold for the latent sharp images, deep learning-based method looks for solutions on a certain search space that may intersect with the manifold. But it's not guaranteed that the solution will be on the latent manifold. Therefore, result might look sharp, but it's unrealistic. On the other hand, physics-based deep learning model has different search space, but the result might deviate from the manifold because of reigning artifacts, wrong blur kernel estimation, etc. So the idea of this work is to apply the model-based constraint to fine-tune the deep blur network so that the final output will arrive at the intersection of those search spaces and the latent sharp image manifold, which corresponds to sharp and realistic images. Since the constraints are based on the image formation model, such fine-tuning process can be done through self-supervised learning without any extra training data. So now let's take a look at our proposed architecture. So for conventional deep learning-based deep blur, one would train the deep blur network using blur-sharp image pairs. At the runtime, you pass the blur image in, and the network will spit out a some sharp images, and it stops there, regardless if the output image is close to reality. So at a high level, the main idea of the proposed framework is that on top of the deep learning-based deep blur network, we propose a new consistency requirement that's based on the physical image formation model. Such image formation model will reblur the output deblurred image. If the output deblurred image is close to the latent sharp image, then reblurred output from this model should be close to the original input blurry image. And by comparing the reblurred image with the original blurry image, we can get a loss. We then backpropagate the loss to update the deblur network to generate more realistic output. In order to make this backpropagation happen, we need to make the image formation model differentiable. And meanwhile, since such loss function is calculated without supplying ground truth sharp images data, such network fine-tuning procedure is therefore done through self-supervised learning. Now let's take a look at the detailed implementation of the framework. So first of all, a sequence of blurry images will be fed into the deblur network to generate sharp deblurred images. And the deblur network could be any generic ones, such as the deep video deblur network by Su et al., which takes a sequence of inputs. Or it could be more recent deblur GAN proposed by Orazio et al., which takes individual image inputs. In that case, we can apply the same network, the deblur GAN network, to each of the input images in the sequence, and then get a sequence of output sharp images. The output deblurred image will then be sent to the reblur model. And the first step here is to feed those images into the optical flow network, which can as well be generic network like FlowNet or PWCnet, sorry. So the optical flow network will estimate the movement of each pixel between t-1 to t, as well as between t to t+1. Now that we have the estimation of a pixel-wise motion, we would like to use it to reblur the deblurred images. We tried two different approaches here for reblurring. The first approach we tried is roughly based on the work by Tay et al. In this approach, pixel-wise blur kernels are generated from the optical flow field. So in particular, Tay's model assumed that at each pixel location, the movement of a point can be approximated as a linear movement. And the blur kernel of a point in the latent sharp image at time t are contributed half from the point moving from t-1 to t, and half from t to t+1. And that's why you see eventually you will have a two-part blur kernel there. So this method uses the delta function to model the linear movement. However, delta function is not differentiable. So in order to tackle this problem, we designed our own blur formation model. Essentially, the model's job is that given an estimated flow UV, and we need to generate some blur kernel K. So the first idea we tried was to train a network to learn the correspondence between the given UV flow and output kernel K. But interestingly, we tried to train two different types of a network, but in both cases it failed because the model eventually converged to the mean flow of the original input training data. So instead, we built a lookup table that at a given UV integer location, which represents the flow field, the lookup table will provide a vectorized blur kernel. Then for arbitrary UV flow, we use bilinear interpolation to sample the corresponding blur kernel. And this bilinear sampling step is differentiable. So repeating this step for each pixel location, we now get a pixel-wise blur kernels. And then we use that, we convolve the blur image, with deblurred image with this estimated kernels to get the final reblurred image. The second blurring model we explored is to warp the sharp image according to the flow field, then average over warp the image to get the reblurred image. In this approach, the flow vectors at each pixel location are subdivided into smaller vectors of a smaller time scale. We then warp the image using each of these sub-flow vectors, and then finally average over all the warped image to get the reblurred image. So for either reblurring approach we are using, we'll finally get the reblurred image. And this reblurred image from the physical model will be compared against the original blurry input. And the idea is that if the deblur network is generating physically correct image, then the reblurring it should result in some blurry image that's close to the original blurry input. Finally, we will propagate this reblur loss to update the network. So putting all the pieces together, we now have the complete pictures of our proposed reblur to deblur framework, where at the front end, you have a data-driven deblur network outputs from this network will be passed down to the physics-based reblur model. And the reblurred image will then be compared against the original blurry input to generate, against the original blurry image to generate the self-supervised loss. And finally, fine-tuning of the deblurring network is done by back-propagating this loss to update the network. So now let's take a look at some results. So the dataset used in the evaluations are from previous papers, including the deep video deblurring network by Su et al., the deep multi-scale CNN deblurring by Tay et al., and the handheld video deblurring via Fourier aggregation by Deblurring et al. We will note them as DVD, MCD, and WFA respectively for conveniences. On top of that, we've also built a small data set of a moving ISO resolution chart to better understand the deblurring performance. So for MCD, DVD, and our ISO chart, we all have a ground truth. And the sharp image in those data sets are captured by a high-speed cameras with at least 240 FPS. And then the corresponding blurry images is generated by averaging over multiple sharp frames. WFA, on the other hand, are captured using only normal handheld cameras without the ground truth sharp images, therefore can be only used for qualitative evaluation. So for the experiment setups, the two baseline network we used are DVDNet and Deblurring. We trained the baseline network, the two baseline networks, on the MCD training split and performed the testing on the test splits of MCD, DVD, and ISO chart, as well as WFA. So now let's look at some result images. Now take a look at this result. In this example, please look at the deblur results on the building images, especially around the window corner and also the pole. In the baseline deblur again results, there are unreal artifacts or saturated colors around the windows. Moreover, even though the pole looks very sharp, there is only one single pole. After our reblur fine-tuning, the window structure become more natural. And we are able to reveal that there are actually two poles over there. And this is consistent with ground truth. Let me flip the image back and forth so you can see it. So in this example, please pay attention to the person's face and as well as blinds. So the baseline deblur puts a lot of high-frequency info on the blinds, and the face kind of looks weird with some high-frequency stripes and saturated colors. And our fine-tuned network are able to remove those artifacts on the blinds and produce a more realistic face, which is, of course, is closer to the ground truth. And in this scenario, we can take a look at the number plates and also the tail light. The baseline result definitely looks pretty sharp, but the number appears to be 1, and the tail lights are very slim. And the bus image, if examined closely, I'm not sure if you can see it from this projector, has some fine grid artifacts. And the fine-tuned network are indeed a little bit more blurry, but we can still tell the number is probably 3 rather than 1. And the tail light is wider. And we found that it's actually the case with the ground truth that for our reblurred output. Okay, so for the resolution chart, the high-frequency artifacts can be seen around the numbers and the fine stripes for the baseline network. And our fine-tuned network makes the number and pattern looks more natural. And in this case, okay, look at the poles around center and on the right, the entire pole, maybe not just squared areas. They seems to be a little bit distorted with artificial curves and textures for the baseline. But the refined networks result, which might not be that obvious on the projector, but yeah, it's closer to the, maybe closer to the ground truth. And in this scene, high frequency texture should appear in the latent sharp image. The baseline indeed looked kind of sharp at the first glance. Okay, I guess for this case, the projector is completely blowing out the fine grid artifacts. But for our fine-tuned network, we are able to kind of trade off a little bit sharpness for more realistic output. And finally, for results on the WFA dataset, where ground truth is not available, we can feel that high-frequency artifacts from the baseline network on the face, the wheel, and the leg, and they are reduced in the fine-tuned network. Okay, so quantitatively, without additional training data and inference time, we're able to achieve about 1 dB improvement in PSNR and about 1 to 5% improvement in SSIM for our fine-tuned network over the baseline network. And we were able to find it is consistent with a different baseline network structures, such as DVD-net and also Deblurring. Such improvement might sound small, but it's quite noticeable of an improvement given the mature stage of the research in motion deblur. So finally, let's take a look at some visualization of a network. So visualizing the baseline and fine-tuned network using a technique called guided gradient backpropagation saliency, we can see that the baseline network has more kind of bipolar response, which might be associated with the high color contrast results you've been seeing. Also near the window area, the saliency response looks more spurious, which kind of agree with the fake details in those areas. Also, recall that we have two networks in our framework, the Deblurring network and the optical flow network. If we choose to update both networks with the self-supervision loss, we can then also visualize the optical flow network output and try to see what it does to the optical flow net. We found that the reblur refinement also helps to improve the optical flow output as well. In this case, the motion is dominated by camera motion, so the optical flow is expected to be uniform across the view. And as one can see here, our refined network helps you to get a more accurate optical flow estimation, besides providing a more realistic deblurring result. Okay, so now for the limitation. There are some limitations with the proposed framework. First, the baseline network needs to work to some degree, otherwise the whole reblurring process is not that useful. And secondly, the current model cannot handle motion boundary very well. So in this example, the DVD-net baseline network does not deblur the image too much. As a result, our framework won't help that much as well. And here we show an example of a motion boundary issue. We synthesize a ground truth blurry image using some arbitrary defined optical flow. We then input the sharp ground truth image into our reblur network. We can see that on the top, the optical flow estimation works kind of poorly at the motion boundaries. As a result, we see discrepancy at the motion boundaries for the final reblur output. You can see those white edges. So looking into the future, we hope to enforce even more constraints, maybe geometric constraints when multiple camera setups is available. For example, seeing motion in 3D space. If the same motion is viewed from different camera, the motion blur should be different accordingly. And we can use that as a geometric constraint as well. So in conclusion, we propose a new framework that bridges the gap between the data-driven deep learning and physics-based image formation model to work on the problem of motion deblur. So, and without additional training data and inference time, we are able to fine-tune the network to generate images that satisfy the realistic image formation model besides looking sharp. We hope the overall idea of our framework, leveraging both image formation model and deep learning, can be extended to further other computational imaging problems. Thank you.
Questions? Yep.
So I had a comment and a question. The comment is that if you set up the Deblurring problem as a minimization of the loss, and then use some kind of iteration, fixed point or gradient descent, it will always involve reblurring the image in every iteration. So in that sense, the concept of reblurring to deblurring is fairly standard. The second question is, I'm wondering if you're aware of iterative batch rejection. This is the method that was introduced about 20 years ago by Iranian Talebi in the context of super resolution. That's basically what you presented there. Are you aware of that?
Yes, I actually saw you guys' posters out there. I'm gonna, maybe we can discuss in detail.
Not my poster.
Oh, okay. You're not from Iranian's group? I'm sorry. Okay, yes.
I'm not promoting my own work. I'm just
okay.
wondering if you're aware of this.
Yes, at the time of a publication, we are not aware of that idea, but I think it's definitely something worth trying in the future. And,
Like I said, it's 20 years old.
okay. Yes.
Would a technique like this also work when you have sort of a temporal blur like one shutter?
Yes. So the idea is that the optical flow should be able to model this kind of movement. So in that case, if you can model this type of a movement accurately, regardless what reblur model you're using, as long as that can model your pixel, your blur accurately, then you can use this framework to improve the result.
Okay. Let's thank the speaker. Thanks.
Thank you.
Thanks, George.
Okay, thank you very much everyone for staying for the last talk, and thank you very much to the organizers for giving me the opportunity to speak. I'm going to talk about estimation of modulation transfer functions directly from real photographs, and this is, hang on. This is joint work with my colleagues Valentin, Michael and Bernhard, all at the time at the Max Planck Institute in Tübingen, and Michael and Bernhard are now fully or partially also involved with Amazon research. Okay, the question that we try to answer is, how good is your camera lens? So if you go on your favorite website and you buy your favorite lens that you always wanted to have, and now it's sitting there on your desk, you want to answer the question, how good is this lens? And typically we know that lens quality is determined largely by optical aberrations, and so if you go into the town of Tübingen and you take a picture of the town hall, you will see that the optical aberrations are spatially varying. Typically for many lenses, the blur in the center of the image will be quite small, while on the outskirts you will see that it's much larger. So in the corners the image is deteriorated much more. And a way to visualize this, as you well know, is the point spread function, which helps us to characterize optical aberrations. However, it's spatially varying all over the place, and so hard to actually compare once you want to numerically estimate something. And so a related and normalized quality measure that's often used in practice is the so-called modulation transfer function, or MTF for short. So what is the modulation transfer function? For this we take a look at this example plot, where I show here in the top a sinusoidal stripe pattern with different frequencies, and you see that the contrast for this top plot is always the same. It always varies between the same minimum and maximum value. Now if I blur this sinusoidal pattern with a homogeneous blur, I will notice that the contrast deteriorates for higher frequencies. For low frequencies there's almost no change, while for high frequencies it does deteriorate quite a lot. And so if I actually just look at the relative contrast, I see that it stays constant in this upper plot for perfect contrast preservance, while in the lower case it deteriorates from a large value to almost zero. And if I now normalize this, this is exactly what the modulation transfer function is. And so here's a more explicit plot showing the modulation transfer function explicitly versus the frequency, and the frequency is measured in these line pairs per millimeter, which is the number of black and white stripes that is used per millimeter on the chip actually. Okay, so this is the definition via the normalized relative contrast. There's a second definition of the modulation transfer function, which is via the point spread function that is used to actually blur this pattern. And as you well know, the point spread function characterizes the blur in the real space or the pixel space, and the modulation transfer function does exactly the same, but in frequency space. So it's related to the point spread function via this Fourier transform, and then the MTF is just the modulus of this, or just the modulus of this Fourier transform. Now this is only for one particular point in the image, because we only use homogeneous blur, and before I've shown you that the blur is actually spatially varying across the field of view. And so now we need to aggregate this over the entire field of view to kind of get a full understanding of how good this lens is over the entire field of view, and maybe not just in the center or one particular location. And so here I show you 3 different locations ranging from the center to the top right corner of this image, and the corresponding local MTF graphs where you see the modulation transfer function versus frequency, and you see that it deteriorates much quicker in the corners and it stays much flatter in the center. And now we want to aggregate this, so we take a plot where now on the x-axis I'm showing you the radial position ranging from the center to the top right corner, and then we can actually just aggregate these plots by taking the plot and discretizing it at certain fixed frequencies, and then just plotting these frequencies in here as color. So now we lose the frequency information in the x-axis, but it's retained in the color at these discrete frequencies. And then you can just take these 3 plots at these 3 different positions and put them into this plot. And this is how you get these so-called global MTF charts, which summarize the quality of your lens over the entire field of view, ranging from the center to the corner. Okay, one question that is, so the point spread function that we've seen before is a 2-dimensional object, but here I'm only talking about 1-dimensional slices all the time. So in which direction should we actually measure the modulation transfer function? And for this, because of the first order rotational symmetry of a camera lens, you typically look in the radial and in the tangential direction. And so these blue and red stripes here are hypothetical line gratings that you could use to measure the modulation transfer function in these 2 directions. And obviously the radial and tangential direction will change depending on where in the image you are. And here in the bottom I show you some measurement results just to give you an idea. So here's again a cartoon showing that we're going from the center to the top right hand corner. And then the modulation transfer function at 4 different distinct frequencies. And then the 2 directions are shown in 2 different line styles, the radial modulation transfer function in dashed lines, and solid lines, the tangential one. And so this is just an understanding for the plots that I'm going to show you later on. Okay, the nice thing is, if you now want to know how good your lens is, that lens manufacturers typically provide these charts. So before buying, you can actually look at this, and typically they will look something like this for a Canon lens, where the axes are exactly the same as before, so MTF versus the position in the screen. The color coding is slightly different, but that's the only difference in these plots. So is this the answer? No. If you look into the literature, and for example, this paper by Dube et al. From last year, you will see that they actually do a lot of measurements, and they find that the modulation transfer function varies a lot between different specimens of the same lens. So if you buy the same lens 3 times at your favorite retailer, and you take these measurements, then 1 might be really good and 2 might be not as good, or there might be some variability. And also typically these lenses are surprisingly asymmetric, and I think they say that only about 10 to 20% of the lenses actually are nice and symmetric, while most other lenses might fall off much quicker to one side than to the other. And so what you actually want is the MTF curve, or the global MTF chart for your particular lens, and not just for any lens of the same type. So how is this typically done? There's a lot of techniques to measure lens quality, to assess lens quality, or to obtain the modulation transfer function, ranging from very simple methods like just looking at test images or at scenes that are typically shown in magazines that compare lenses, to extremely complex and expensive methods like analyzing the entire wavefront, or what Dube et al. They use these professional MTF testing stations which set you back $50,000 or even more. And in between are methods that use MTF test charts, and I think those are most widely used and implemented in many different software packages, and there's also a range of different techniques that these software packages use to actually obtain these measurements. But all of them have the problem that they do require additional equipment, and they're quite time-consuming and expensive to use, because you still need to buy these charts, you need to buy lighting, you have to set everything up, you have to know how all these things work. So a typical hobby photographer who just wants to know how good his lens is doesn't have this equipment. And this is where our work comes in. We provide a new method which basically takes a stack of unprocessed images, then you feed it into our learning system, and out comes this global MTF chart that you can then use. And in terms of quality of the results, we don't try to compete with these super state-of-the-art expensive techniques, but we just want to give robust information to hobby photographers who want to evaluate how good their lenses are. And the intuition behind why this should work is that photographs actually do contain a lot of information about the lens. We saw in the beginning that in the corners it's much more blurry than in the center, and somehow you should be able to quantify this. Unfortunately, the information is confounded with the image statistics of these unknown scenes that we've captured. But luckily, if we use the same capture setting for all of these, the point spread function at a particular location in the image will always be the same. And so, for example, in the top right-hand corner, all of these images, if I've taken them with the same lens at the same settings, will have the same blur, although the content of the image might, of course, be different. And so this is how our learning system is structured. It's basically consisting of 3 parts. First, we extract some patches and pre-process them in some way. Then we perform a local estimation of the modulation transfer function just in this patch. In the second step, which gives us these discretized values, and then we globally aggregate them over the entire field of view. This local MTF estimation will be done with a convolutional neural network and then some fully connected layers that kind of regress into these outputs, while this aggregation will be done, in our case, with some Gaussian process regression, but you could use any other form of regression technique to just accumulate the values and smoothen them to a certain degree. Okay, so how does this neural network architecture actually look like? So we start with image patches with a single color, because we do treat the different colors channels separately, because chromatic aberrations will mean that the aberrations are actually, and the point spread functions are actually different in the different color channels. So in comes an image or blurred image, and out comes the modulation transfer function discretized in both directions. And actually what we do is that we don't let our network predict in both directions. We actually train our network only to predict in one direction, and then to obtain the other. So for example, just this upper path here. And then what we do is we flip the image by 90 degrees and pass it through the same network a second time. And this will give us the modulation transfer function in the orthogonal direction. And this allows us, or we observe that this improved training and generalization quite a lot, because it will not get fooled by correlations that might be in many of the blur kernels. Okay, then we do this pre-processing where basically we already discussed this rotation, then we append the image gradients in the direction where we want to estimate the modulation transfer function, and then similar to what Paolo Favaro was mentioning before, we subsample the image into channels to increase the field of view that the convolutional network will see. And then we have a convolutional network that consists of several resonant blocks, gives us an intermediate feature representation, which is here shown in lila, and then is mapped with some fully connected layers onto the outputs, where the outputs would be then in just one direction, and as I said, we pass them on, through separately. And now the question is, okay, what do we do if we don't have just a single image patch, but we have several patches from several images? What do we do in this case? We follow, or we basically pass all the images or image patches through the network separately until the intermediate feature representation. So after the last convolutional layer, then we average in feature space, and then we pass this average through the fully connected layers onto the outputs. And this is an approach which has been formalized by Sahir et al. In this deep sets paper at NIPS 2017, but I think this idea of averaging in feature space and learning a feature space where adding and averaging is more useful than in the output space has been around for a long time. Okay, now we need a training set for this neural network, and for this we use synthetically blurred patches, so we also set up a synthetic supervised training task. By synthetically blurring, we do know what the ground truth modulation transfer function for that blur should be. And so we can just train the system with these blurred patches where we know the output, and then just use an L2 cost function, which I haven't even written down because we really just use an L2 cost function between these output values and the ground truth values. So what's the data that we use for this? Well, we need sharp ground truth patches, and we need lens blurs. For sharp image patches, we use either a regular test pattern that has been introduced by Yoshi et al. In 2008, or we use patches from real photographs that we've taken in the wild, and there we took a really good lens which has very, very small blur kernel and a very large f number, but not too large, so that we're not limited by diffraction. And then we downscale the images and we only take pictures or patches from the center of the image so that they're as sharp as they can be. And for lens blurs, we use artificial lens blurs, but we also record a lot of lens blurs with a custom pinhole array that I'm going to show you on the next slide. So namely, we built a pinhole array which is 1.5 times 2 meters large. It's basically an LCD panel which is backlit, and then has a large photographic black film which is developed to have these little small holes. And in total there's about 4,800 holes, and by taking a picture with our camera of this screen, we can capture the point spread function over the entire field of view at a certain camera setting with a single photograph. And we do actually take several photographs and then average them to increase the signal-to-noise ratio, but this allows us to capture and characterize the ground truth very efficiently. So we take about, I think, an hour for a single lens under several settings that we do. And this can be set up and done automatically more or less once we set up the camera. And we'll provide this data set for several consumer lenses that we recorded on our project website. Okay, so now this is all the setup. Now I want to come to the experiments and the results and show you how our system works. And basically we're looking at 3 different types of experiments. First, we do a kind of sanity check. We use synthetically blurred patterns just to see that the system can actually work on data that has been processed in the same way as the training data, but with blur kernels that it hasn't seen before. Then, as a second check, we look at printouts of this test pattern at different scales, and then take photographs of this very similar to a setting in which you would do MTF test charts. And then in the third case, I'm actually going out into the city of Tübingen and just taking lots of pictures of walls and buildings and then feeding them into the network. And the results that I'm going to show you are all for one particular lens. They're not cherry-picked, but I want to be consistent and make it easy to understand. In our paper in the appendix, we do have a couple of lenses to show that the results are actually transferable also to other lenses. Okay, so this is the results for the test pattern. We're here in the center. I show you the ground truth values that I've also shown you in the beginning. And then here on the right-hand side is the plot where we do synthetically blur the images with the blur kernels that we recorded from our test panel and from which this ground truth data actually comes from. And then you see, and if you compare the two, you see that they're almost identical. So our system does a very good job at reconstructing this from synthetically blurred images. And then here on the left-hand side, I again show you the modulation transfer function versus the radius. I should have mentioned this before. So we go from the center to the top right from real photographs. So I actually took several pictures at different distances and then cropped them off this test chart. And you also see that these results agree very well with the ground truth data. Then in the second step, we don't only just look from the center to the top right, but actually from the center in all different rays, and then average them over the angle. And again, here's the ground truth and the prediction from our model, and then here I also show the average error, which is typically below 10% of the maximum value. And you see that it agrees qualitatively and also we think quantitatively quite well, although there are some discrepancies. For example, all of these lines are slightly lower than the lines here, and we think this is partially due, for example, to the MTF of the printer used to print this test chart, because obviously this printout will not be perfectly sharp, but there will also be some inaccuracies that come in through the printer. Okay, and as I said, the results are not cherry-picked, so errors for other lenses will look very similar. And now we turn to the results for natural scenes. Here I'm showing you again the ground truth, and again going first from the center to the top right. So these are the real output data, which is quite noisy, and so I split it out into the radial and the tangential part so that you can read it better. And here you see also the Gaussian process fit we use to kind of smoothen the data out and then compare them. And if you now look again over the angular average, you see that again the qualitative features are met quite well, so the kind of level in which you start here in the center and then it decays towards the side. is quite good, but then you also see that there are some differences in terms of quantitative agreement, especially here in the sides, and you also see it here in the error plots, that the error does get larger towards the corners, and especially our plots don't decay that much towards the corners. And the question is, where do these discrepancies come from? And there's two main sources that we have identified. One is that, which is part of the measurement technique actually, is that you do have curvature of the focal plane, especially at these these very open apertures that we use in our experiments. And when the focal plane is curved, our PSF panel with which we record the ground truth is a flat panel, and so parts of the image, especially in the corners, will be out of focus because of this curved focal plane. While if you go outside and you take pictures of real objects, as you know, real objects are not perfectly flat, but they will have some depth variation. And so some parts, especially in the corners, will be in focus or more in focus because they kind of have some depth variation, and so part of this depth variation will be closer to the focal plane than the actual flat panel. And this is why we think that our plots don't decay as much towards the corners as you have in real case, as you have in the PSF panel case when we record the ground truth data. And then the second point is that not all patches are suitable, of course. Objects might be not in focus, so if you have a large object in the front that kind of is not in focus, then obviously this patch is not going to be useful. Also, homogeneous or very textureless regions are not good, so if you take a picture of the blue sky and you blur it, it will look exactly the same. So this also doesn't carry any information about the blur. Or if the edges, for example, occur only in one direction, then it's very difficult to estimate the blur or estimate the modulation transfer function in the orthogonal direction. And we did a lot of experiments in this direction and show them in the appendix of the paper as well. And the mitigation strategy is to kind of circumvent these problems as much as possible. So as I said, the first part we can't really circumvent because it's built into the method in some way, is that we select this, suitable photographs by hand and suitable motifs. So when I go out into Tübingen and take pictures, I try to take as planar scenes as possible and as scenes that have a lot of structure and a lot of texture everywhere, to avoid having a lot of sky, for example. But if you want to move forward into, for example, a production system, then you would actually need to automatically select photographs or patches that you want to use in this estimation. And for deblurring or PSF estimation, Hu et al. In 2012 had this paper, Finding Good Regions to Deblur, and we think that a very similar approach could be used in a production system to improve results even further. Okay, with this I want to conclude. So we present a system for the automatic estimation of the modulation transfer function directly from real photographs. It consists of 3 parts. We first extract patches and estimate the MTF locally in these patches, and then we aggregate this information into a global chart. Starting from the stack of images, we can actually estimate the modulation transfer function or the entire chart within a minute or two on a modern GPU, even for a 50 megapixel image that we used in these experiments. There's a good qualitatively and we think reasonable quantitative agreement with the ground truth data that will help photo enthusiasts who don't have access to equipment to appreciate and understand the equipment better. And we also built this panel with which you can record real point spread functions and optical aberrations for aberrated lenses, and we'll make this available on the project website. And now I'm happy to answer any questions, and also I'll have a poster about this, so you can also come and see me at the poster session if you have more in-depth or technical questions. Thank you very much.
Questions? Yeah.
Do you distinguish between sensor active and lens active? How do you separate the two? And then do you compare standards like Imatest or some other?
Yeah, so this is a point that I kind of swished under the carpet for a bit. So all these techniques that basically I've also shown in this table here will typically measure the joint modulation transfer function of the lens and the camera as a whole system. And we do the same because we can't separate out the lens and the camera, and so I should have said probably more honestly that we estimate the modulation transfer function for this joint system. And we also do have a comparison to other methods, so other photometric methods here, where basically these dots are measurements with a test chart, and we use this tool by image engineering, and we evaluated both on Siemens stars and on slanted edges, and we do find this a good agreement between the measurements in general. So both the measurements and with our ground truth panel and kind of what this IMA test or image engineering do give us.
Nowadays we're seeing on Schölkopf, for example, post-processing through deep nets. You can't, assuming you can't get the raw image before that post-processing, would this model still make sense for the corrected images afterward?
This is a good question. I think there's a couple of papers now recently coming out discussing especially this point, and I think there's also been a lot of old papers wondering about the MTF of, for example, JPEG compression. And basically the result is that you can't use these images to reliably get information about your optical system, because the MTF is very sensitive to all of these features, and especially sharpening effects will actually increase the MTF to values larger than 1. Because you do get actually sharper corners and larger contrast than you actually had in the original image, even before blurring, and this will basically make it impossible with processed images. That's why we always talk about using unprocessed photographs in our system.
When you established the ground truth, you use 1 Siemens or 9 Siemens targets, so you do the corner distribution?
So we do have, these test charts basically have an arrangement, I think, of 5 × 5 Siemens stars over the entire field of view, and then so that gives you 3 Siemens stars, 1 in the center, 1 in the middle, and 1 in the corner, and then we average this over the results of all these stars to show in the result. But as you say, the problem with these test charts is also that they don't measure the modulation transfer function at very many points, and they interpolate a lot or average out a lot, and especially in the corners where the deterioration is strongest. There typically are no slanted edges or Siemens stars directly in the corner, but only somewhere in the region, but this region is quite large, and if the fall-off is quite steep towards the corners, then you don't get this with these current measurement techniques.
I think we had one last question, so yeah.
Yeah, I was wondering, what do you think might be the impediments to using this for characterizing mobile imaging systems that are already embedded into your system?
I'm not sure I understand your question.
So, can you do this same analysis with cameras on cell phones?
If you're able to get raw and unprocessed images, which I think for some sensors they do actually give you access to kind of raw images, then yes. But if you only have access to post-processed JPEG images, then I think it's quite difficult. And I think this is the same problem that also applies if you would do tests with a normal test chart.
What about positioning of the devices and those kinds of things? Because these are a little harder to handle rather than a big video camera.
That's true. So I mean, I guess you have to ensure that, as I said, we try to select scenes as planar as possible, and then to kind of also capture them as parallel as possible, so that you don't have some defocus due to misalignment. But if you take a large enough object like a house or a brick wall or something like this, which does has texture everywhere, and you position yourself roughly, then it should be more or less good enough, I would say. But I think that going forward to build a production kind of ready system that does this reliably, you would need to kind of come up with a scheme to determine whether you are in focus or out of focus, for example. Without, obviously, I mean, there will be some optical aberrations that you don't want to filter out, so you have to be careful on how to design this, and this is why we haven't done this in this system, because we think just doing a naive approach is probably a bit difficult, but using, for example, this approach and then refining it for this setting might be quite useful.
Right. Let's thank all the speakers, and we have a